Just wanted to say a very warm welcome to everybody. This is our third News from the Lab. So we've moved from CMS now to, can I say its rival, Atlas? Hang on. Is that allowed? Am I allowed to say that?
You can say it.
Yeah, it's fine.
Okay, I'm just going to... All right, sorry. So, very warm welcome to everybody. And we're now, as I said, moving forward. This is the third News from the Lab. We're going from CMS to its rival, Atlas. Now, for those alumni that are connecting today and connected in the past, this is a great way for you to reconnect to the organization, for us to bring you back to CERN, at least virtually for the time being. I'm delighted to introduce our speaker today, who is Kostas. We've got his full bio on the event page on alumni.cern. So Kostas has been based at CERN and working in the Atlas experiment since 2011. He recently, amongst many roles, he's recently taken on the role of run coordinator for Atlas muon detector system, which is mainly focusing on the integration of the new small wheel within the Atlas experiment, which is what he's going to talk about today. And Kostas is joined by Florencia, who first came to the Atlas collaboration in 2014 as an undergraduate student. She has since obtained her PhD, so she's since obtained her PhD and now dedicates her time, still with Atlas, to working on searches for new physics, looking for evidence of processes that are not explained by the standard model. And again, there's more of her bio on the event page. So the way these events work, we have 30 minutes of, the talk is 30 minutes more or less with Kostas, and then we hand over to Florencia, who's going to moderate the Q&A session. So I'd like to say a very big thank you to both Kostas and Florencia, and thank you to you for joining. And I'll speak to you in a moment. I will be also sharing a link for a survey, post-event survey, if you'd be so kind as to complete that, and also let us know if there's any areas or sectors within CERN that you'd like us to feature the next time. So Kostas, please take it away.
Thank you very much for the introduction. Let me try to share. Does that work? Perfect. Perfect, thank you. So, hello to everyone. It's been it's great to be here and talk to you about this this project, which is called the New Small Wheel, and it's an upgrade project for the Atlas experiment. Before going into the details of the project, I would like to make I have some introductory slides. So, starting from the LHC. Okay, probably most of you know, but it's a two-ring hadron accelerator and collider, can collide protons and ions. 27 kilometers in perimeter tunnel, which was initially built for LEP in the 80s. The accelerator is made of thousands of magnets that are superconducting, so they have to be cooled to less than 2 Kelvin. And it has a center of mass energy by design of 14 TeV. And it collides particles in bunches spaced apart of 25 nanoseconds. So we have nominally about 2.8 K bunches with 10 to the 11 protons per bunch at the start of the fields. And it has a design instantaneous luminosity, which basically is a measure of number of collisions per square centimeter per second for the experiments like Atlas and CMS, which is at the order of 10 to the 34. And the machine has been working great over the last year. So since 2011 and until 2018, when we had the shutdown that started then, Atlas has recorded quite a lot of data, about 147 inverse femtobarn. The collider has been working well, but the plan is to upgrade it further in order to increase its discovery potential. It's what we call the high-luminosity LHC. And this will deliver 5 times more collisions per bunch, which will result in an increase in the luminosity by 7, the order of 7. You see, we go to 7, 10 to the 34. And this upgrade is happening in phases. So currently we are in phase 1, which is here what we call the long shutdown 2 that we are currently in, which ends at the end of 2021. And then there will be a second phase, the LS3, in 2025. And after that, we will be in the era of HL-LHC. So this increase in the number of collisions per beam bunch, of course, means increasing the rate of the particles that go through the detectors of the experiment. So this require major upgrades for the experiments that need to be able to cope with these conditions. Would like also to introduce you a bit to the ATLAS experiment. So the ATLAS experiment is a general purpose high luminosity experiment at the LHC. And it carries out precise measurements of elementary particles and also makes discoveries like the Higgs boson. It has a cylindrical structure with several detection layers. You can see here this 3D drawing of the detector with the different detector types depicted here, like the calorimeters, the inner detector, and on the outer part, the muon chambers. It also has a superconducting magnet system, the solenoid and barrel and captoroid magnets that you can see again in this 3D drawing, which are used to bend the charged particles so that we can measure their properties and more precisely their energy. And each of the detectors has a specific job to do. So as you can see, for instance, in this sketch at the bottom right, depending on the nature of the particle and its properties, it interacts differently with the detectors. So it may stop and deposit all its energy in the electromagnetic calorimeter. If it is a photon or an electron, if it is a proton or a neutron, it will stop in the hadronic calorimeter. If it is a muon, it will not stop at all, but it will just pass through our detectors and induce signals on these detectors so that we can track it. One very important ingredient of the ATLAS experiment is the trigger system. It's really critical because it is impossible to reconstruct and store all this data that are produced from the collision. So we cannot save all the events, and we need a system to filter out the events that are not interesting for physics. And in ATLAS, we have this trigger system is built in 2 levels. And basically what it does is that it performs fast processing of the data from the detectors and makes a decision if this event is interesting or not in order to process it and store it. So with this filtering system, we go starting from 40 megahertz, which is the rate of the collisions. We go after the first level of that to 100 kilohertz, so quite a reduction there. This first level trigger is done in hardware, so we have custom-made boards with FPGAs that are installed in crates, in racks that do this fast processing at the first level. And then the interesting events go to the next level where we have the high level trigger, which further reduces by 2 orders of magnitude the rate. And this processing of the high level trigger is done in CPU, so in computers. And you see here a sketch of the trigger system, the architecture in ATLAS. It's a bit complicated. I don't want to go into detail now. The important thing is that these decisions need to be issued very quickly. So, for instance, the level 1 decision is issued within 2.5 microseconds, while the high-level trigger decision is issued after 500 milliseconds. And this is extremely fast if you compare it with our, let's say, offline reconstruction, which takes about 30 seconds. So this is what I mean. This needs to be happen fast. So going now into the system that is of interest for us, is we will be talking for the new small wheel. The new small wheel is part of the Atlas muon spectrometer. The current system, the current muon system, is composed of 4 different detector technologies: CSCs, MDTs, RPCs, and TGCs, all gaseous detectors. You can see here again a 3D drawing that shows the different chambers and detector types with the different names. We have, of course, small, large sectors and detectors. That's why you see these different names. And the main work of the muon system is to measure the momentum of the muons that pass through the detectors. And this is done by calculating the curvature of the track, which is happening due to the magnetic field. So to give you an idea, at the bottom right 3D drawing, which shows again, 2D drawing, shows a cross-section of the spectrometer, actually a quarter of that. If this orange track goes through the detector, this is a muon, it is bent. And then what we do is that we measure the deviation from the straight line, which gives us an indication then of the energy of the particle. This is the basic principle. And we can do this with an accuracy of better of 10% for energies of 1 TeV. And it's important also to note that of course, after a lot of tuning of the muon system over the last years, we are able to reconstruct the muons with an efficiency above 98%, as you see it distributed along the full coverage of the system, which is a very impressive result. In order to achieve this, we rely on the alignment system of the muon spectrometer, which is really necessary in order to be able to achieve this accuracy. Because as you understand, we are talking about here detectors that are very large. So it's very important in order to reconstruct the track precisely to know exactly where its detector is, its chamber within the Atlas coordinate system. And it's really a very big challenge to align these huge and very heavy objects. Their size is larger, is order of magnitude larger than the precision we are trying to achieve. And for this reason, we have an optical alignment system that basically keeps track of the movements and the deformations of these detectors. It's based on cameras. You see here on the right, these sketches give you an idea of the optical lines that go between the sensors in the system for the barrel and the end cap regions. And basically calculates constants for correcting the position of the detectors. You can see some of them a bit exaggerated on this figure at the bottom in the middle. And these then are applied to the offline reconstruction that we do when we are trying to reconstruct the tracks. And again, it's really impressive that with this system, we are able to align the chambers within with an accuracy of 50 micron, 0.05 millimeters, which is basically what we needed to achieve the accuracy in the muon reconstruction. So going now to the new small wheel, a bit on the motivation of it, why we need to upgrade. So this is one of the largest upgrades. Atlas has other upgrade projects, of course. What it is about replacing a part of the muon system, which is called small wheel. You can see there are actually two wheels that are shown in this, again, 3D sketch, with new wheels, with new detectors. And why we need to do this? One reason is that the performance of the current detectors is limited and will be further limited with the increase in the particle rate. So, for instance, one of these detectors that you can see on this photo, actually there are 3 detectors in the small wheels. The MDTs are expected to have an efficiency that will be 50%. At the rate we're expecting at the LHC. So it's really, they cannot survive the rate. They need to be replaced with detectors that are high rate capable. This is one thing. The second thing is the trigger. Currently, the current trigger system for the muons is only using information from the big wheel that you can see at the bottom in the middle plot. Processes the data that are coming only from the big wheel, and it doesn't have any information from the small wheel. And we have a lot of fake muon triggers generated because we have other particles that are passing through the big wheel with, let's say, a track that is fakely pointing to the IP, to the point of the collision. However, these are really fakes because they are not coming from the collision. These are other particles from background. And what we need is we need to install this new detector and integrate it in the trigger so that we can have this extra confirmation point from the small wheel region, so that we can, have a coincidence of the big wheel and the small wheel, and we can then extrapolate this to the IP so that we can kill all these fake triggers, which you can see on this plot. Are dominating the area are dominating the triggers in the end cap area above pseudo rapidity of 1, which are these yellow distributions which need to be suppressed. So small wheels, but actually these wheels are not really small. They are half in diameter compared to the big wheels that we also have in the experiment. But they are not small, so they are 10 meters in diameter. They are really big. So this project was initiated in 2007. And at that time, of course, there were proposals for different detectors to use for the new small wheel. We had, you see here, SMDTs, sTGCs, some small gap RPCs, improvements of the detectors of the legacy system, and also the Micromegas, which was a new detector at that time. So we went basically for a few years. There was sort of a competition, a race between the different technologies, trying to prove their detector is the best choice for the new small wheel, demonstrating the performance or using Mr. Clooney here to advertise that Micromegas is the best choice. In the end, it was in 2012, in March, when the collaboration converged to a choice that was sTGCs, small thin gap chambers, and Micromegas for the new small wheel. And the technical design report that specs this project in detail was published in 2013. So the new small wheel detector system, it follows again the same geometry as the old small wheel. So it has 16 sectors separated in small and large, 8 and 8. And it combines 2 detector technologies, as I said, small strip thin gap chambers that will be primarily used for the triggering, and Micromegas with resistive strips that will be used primarily for the tracking. And each of these 16 sectors is composed of 16 detection layers. You can see the layout here, sTGCs on the outer part, Micromegas in the inner part. Basically, we went for this choice to have so many layers as a provision, so that we have redundancy in case we lose a layer or an element of the detector, so that we are still able to reconstruct the muons with a good accuracy. Of course, what this also means is that we have quite a huge detector surface area, which in total it adds up to 2.4K square meters. It's a lot of detectors. And in this blow up here at the bottom, you can see what is the structure of the sector. So in the middle, it has this mechanical structure, which we call spacer frame. Then on both sides of that, we attach the Micromegas wedges. And then we come and we finish this sandwich with the two sTGC wedges on the outer layers. So about the two detectors, few information. The Micromegas is a new detector. It's a novel detector technology that is based on what is called micro-pattern gaseous detectors. And it's actually the first time that this kind of detector is used in such a large scale and also in an environment that has such a high rate of particles. And its main characteristic is that it has asymmetric regions. So we have the drift region where the ionization of the gas is happening. And then we have the electrons that are produced from this ionization that are drifting towards the anodes, which are the readouts of the detector. And then they are amplified in this very small region of 128 micrometers. Before the signal is induced on the readout and we read them out. The advantage of that is that we have very fast evacuation of the ions, which is important for this kind of detectors because you don't want to have a charge forming inside your gas caps because it is changing your electric field. And we can achieve also high amplification with very small, reasonably small voltages in the amplification region. One more thing is that for this detector, in order to be high rate capable, we are using this so-called resistive strips on top of the readout strips, which is a mechanism to protect from discharges. So apart from that, this detector has excellent spatial resolution, so it can reconstruct the position of the particle with an accuracy of 0.1 millimeters. The sTGCs, on the other hand, is based on a well-proven technology, the TGCs that exist in the legacy system, with some improvements like finer strip pitch and also some updates on the resistive coating to improve the rate capability. It's a wire chamber. You can see the internal structure in this sketch. And they have excellent timing properties because they have small gaps and very strong electric fields. So the signals are coming out very fast, and that's very good, very useful for the triggering. But of course, this project is not only about the detectors. Electronics are equally important because we need these electronics to read the detectors out. And these are really custom made because they need to meet the specs and suit our needs. And for this project, we had to develop new readout and trigger chains to be compatible with the Atlas and also its upgrades for high-luminosity LHC. The size of the system is such that we ended up having 2.5 million electronic channels to read out, which is a huge scale up compared to the 100K that we had in the old system, which of course then translates to thousands of electronic boards and that are either on the detector or also off the detector that we use for the trigger and the readout. And you can see some photos of these boards as they are received at CERN, tested, and then installed on the detectors. So after the approval of the project and before we start with the construction really of the big detectors, we went through a long actually R&D phase, both for the detectors and the electronics. And basically we did this because we we wanted to test the performance of detector prototypes that were built with different sizes, properties, and also some different designs in order to finalize the characteristics of the detectors that we will be using in the final system. And of course, for the electronics, we needed to test the different revisions of this. Then during these times, we were also doing studies to understand the performance of the detectors and develop techniques for the reconstruction of the particles that go through the detectors, and test really the performance under different conditions, like, for instance, what happens when you operate the detector inside magnetic field, which will be the case in the new small wheel, or also really test the rate capability of the detectors. And this was an R&D effort that was done for this project, but in fact, the results were interesting also for the larger community, and this led to several publications and also many theses that were done on this. So just to give you an idea, when I talk about R&D, most of it has to do with test beams, where we take the detectors, the different detectors in sizes you see, and we test them with beams. This we did in several places, either at CERN using PS or the SPS accelerator, but as well outside CERN, like in DAISY and Fermilab. So during that period, I think if I counted correctly, we have accumulated more than 50 weeks of test beam time, which is quite a lot. So starting now with the construction of the chambers, we entered that phase at some point. The Micromegas are built in different construction sites spread over along Europe. You see, we have Germany, Italy, France, Greece, and Russia. Some parts of the detectors are actually produced in industry, like the readout PCBs. And they go to these construction sites, and then they are assembled into detectors that look like the one you see in the photo, which is actually the last detector that was made for the new small wheel in Germany. During that phase, with the first modules, we had one of the first challenges of the project, because we noticed that we had high voltage stability issues from the first detectors that were built. Which again, for these problems, we went again through an R&D phase, trying to understand why we have this and how to improve and or solve these problems. In the end, we understood where these were coming from, so we developed techniques in order to mitigate these issues. And we managed to get to produce detectors that finally were rather good. So you see here the efficiency of all the detectors that were made for one of the two wheels, which is above 90%. Similar situation for the sTGCs, which are made, actually, the construction sites are spread over all 5 continents. And again, they are partially industrialized, some parts of it. You see here some photos of how the panels are built, processed, and then are assembled together in detectors. And of course, the detectors, after they are assembled, they have to be tested. So they are tested for either with X-rays or with cosmics, just to validate their performance. When the detectors, these chambers, are ready, they are then sent to CERN, where we mechanically assemble them into the sectors that we will put on the wheel. Here you see photos taken from the facility where we are doing the wedge integration for the Micromegas. You see the different sectors that are being built. And here, basically, it's a production line. So the detectors arrive, and then they go through a series of steps before they are assembled into the sectors that we then send to be attached on the wheel. And it's really a production line here with about 20 people working daily and distributed over the different tasks. And we have managed to reach a pace of producing a sector every 10 days. This is our recent performance. Similar thing has been set up at CERN for the sTGC. You see here a bird's eye view from the area where this integration activity is happening, and here a diagram that shows the workflow. Of course, it's not exactly the same because we have different detectors, so some of the steps are different. And we've managed to have the two production lines synced rather well so that we don't introduce any delays in the overall schedule of the project. Apart from detectors and electronics, one other very important part of this project are the services. So we have, as I told you before, very big detectors, millions of electronic channels, and it translates to kilometers of pipes and cables that have to be installed on the structure of the wheel as well as on the detectors themselves. And always in this kind of projects, we have space limitations. So a lot of effort was put in really optimizing the routing and the placement of all these services. You see that before we start really to build the actual thing, we have done simulations of all this work, where to pass all these cables and all these trays and all the equipment that has to go on the wheel. And this was really a huge amount of work with more than 10 people working on this for years to achieve that. In the end, for the services, it was in autumn 2019 when basically the structure of the wheels was ready with the services to start receiving the sectors. Thankfully, around that time, it was we were getting close to Christmas in 2019 when Santa paid us a visit at Building 191. And this time he came actually with a truck with detectors. So you see here the first wedges that were delivered from the integration sites to the place where we have the wheel structures. And then they went through some mechanical manipulations for a couple of days. And in the end, you see here the sTGCs and the Micromegas wedges side by side. And eventually they were assembled into a single sector that you see on the bottom right picture. This is actually the first sector of the new small wheel that was assembled. And then this sector, you can see here the process where basically this is just the final step where we take the sector with this special tool, which is hung from a crane, and it is prepared and then transported on the wheel. And I hope you realize from that of course also this project has a lot of mechanics involved. So the design and the implementation of all these procedures and mechanisms was also really a very huge effort. So quite a lot of engineering work went as well into this project. And here you see the wheel in the sector in place. And then after that, we had a nice party to celebrate that very close to Christmas. So the first sector, the first small sector on the first wheel. Of course, then at the beginning of 2020, we were hit as everyone else by the pandemic. So we had all sorts of problems with institutes shutting down, access restriction, travel bans. And this slowed us down for a couple of months, but then we ramped up quickly with all the measures in place and trying to optimize the work in order to not to lose time. So you see here the people working in the different areas according to the measures. So then we were able to continue the work. So we continued then with installing more sectors, while in parallel we started commissioning them and testing them on the wheel. And then we had we came across one of the biggest challenges, because at that time we realized that from the first sectors we installed, we had quite excessive electronics noise. which was not understood. And at that time, another R&D effort was initiated, trying to find a recipe to mitigate this problem. In the end, we understood the problem, we developed a solution, but what this meant is that we had to take down all the sectors that have been already installed. You see here on September 2020, we almost had all the small sectors installed on the wheel. We had to take them down, disassemble them, refurbish them to solve the issue, reassemble and reinstall. So this took us about 5 months to get back to the point where we were before. So it was a big challenge. Fortunately, after this refurbishment, the installation and the commissioning of the sectors has been going smoothly. This is the latest situation where basically we have 3 more sectors to install in order to finish the first wheel. And the plan is to have it ready by mid-June. We have, of course, a second wheel to build, which is we started already to work on that in parallel with the first wheel, and this is expected to be ready in autumn. And then, of course, we have to proceed with the installation of this in the experiment and the commissioning. So we start to see the light at the end of the tunnel, thankfully. Of course, there are some wise people that warn us that to be careful, because at the end of the tunnel, it may be the train that is coming that is producing this light, but so far doesn't seem to be the case. But in any case, we keep our eyes open. So it's been a very challenging project. So it's quite a journey so far. It hasn't been easy. It's not small. I hope you understood that. And we really, a lot of people working long hours to achieve the results we are currently at. But of course, also it is with these challenges, it has been very satisfactory for us to be able to overcome this issue and see these wheels coming into life. Of course, this is not the end, it's just the beginning, because we have exciting time ahead of us. We will have to transport the new wheels, the new small wheels to point 1. These are some photos from the original wheels when they were built. So we have to go through the same process, mount them on the track, take them to point 1, lower them down with the crane, install them in the detector, connect them, and then commission them with the rest of the experiment and make sure they work as they should. So that's my last slide. Thank you for your attention. I open the floor to questions.
Okay, thank you, Kostas, a lot. This is really interesting, and I'm still, I think it's amazing the amount of work that you have been done for the last, well, I don't know, 10 years since you all first had this idea of the small wheels. So yes. I don't know if there are any questions from people. Maybe you can just go ahead or raise your hands, well, virtually, right? Okay, Loic, I see that you want to ask something. Go ahead, please.
It's Michele first. Who is it? Yes.
Oh, sorry. Yes. Please go ahead.
Who is? Are you referring to me, to Michele? Or
yes.
To me or
to Michele?
Okay.
Yes.
Thanks for this excellent presentation. Congratulations for the result that you have achieved. I would like to testify the difficulties that this project went through, because as a former ILO for Greece, I was involved in the procurement of the DAC acquisition board for the Micromegas chamber to the Greek company Prisma. And also concerning the noise, there was Faraday cage, a small Faraday cage, which was produced by company Rentron to shield power supply. Could you comment on that? The number of data acquisition card supplied by Rentron were 1,000, if I'm not wrong.
You are talking about the ADDC cards that we had to shield with the Faraday cage, right?
Yes, that's correct.
We have 16 of these per sector, so 16 times 32, it's 512 cards for one wheel. So for two wheels, 512 cards. And this was, this was one part of the problem with the noise. We were seeing this noise, but it had inside several contributions. So at the beginning, we thought it was coming from there. Indeed, there was a contribution from the power supply on that board that was emitting noise. We shielded that, so we solved this issue, and then we were left with all the other sources of noise, which we started studying. And then in the end, we had to do corrective actions in several places, like the grounding of the detectors, also some modifications on the power supply and the grounding internally in the power supply, some improvements on cables and connectors. So there were many things that needed to be fixed in order to overcome this issue with the noise.
This solution was found with the help of Theo Geralis, who is my colleague at Demokritos and also now member of Atlas. He was giving right instruction to the company how to create the Faraday cage. Thank you.
Yeah, even for this very simple thing, we had to make a design, make prototypes, test the prototypes. It's also not easy. You have to take into account that this was not included in the original design of the board. So directly you start to have classes, mechanical classes of the cage with the detector. Space is really limited. So it's again, this went through several iterations to get it right.
Also, I have on my office at Demokritos one prototype of this small box in copper.
Yes, I imagine we have here several. Also, I may have here one as well.
Okay, thank you.
You're welcome.
Okay, is there any other question? Please go ahead, you can ask.
So can you hear me?
Yes, we can.
Yeah, so I just wanted to say congratulations to Kostas. This is really amazing, and I really liked to see all these nice things because like Michael also said, since I was a PhD student at Demokritos and also from my master studies, I was working for the Micromegas when it was really in the beginning of this big project, when there were the first test beams. So I'm really...
When they were like this, the small one.
Exactly.
On the top left.
I really loved to see all these things, since now I'm out of business for 4 or 5 years. Thank you very much, Kostas. It's really amazing.
You are welcome.
If there are no other questions from other people, I just would like to make just a mention. Can I?
Yes, please.
I don't know if you know that Greece has given also strong contribution in the construction of the big wheel. All the aluminum bars were produced in Greece. And these were special aluminum. We have made a big effort to fit the specification from Atlas. 40 tons. Partially, Greece supplied 40 tons, but also Israel. Not the small, the big one. I'm referring
yes,
to the
yes,
big
I
one.
don't have a photo of the big one, that's
okay.
why. But the tubes
Okay, so
Michele
you
is
can be
talking
proud.
about are shown here. These are the same tubes.
You can be proud. Greece has given a big contribution because also has equipped with the proportional chamber, all the big wheel. The drift tube, I mean the drift tube.
Yes, yes. The tubes, just for people that do not know, are if you can see in this in the wheels, the outer part of the sector is made out of tubes. It has there are here you can see a layer of tubes, but there are six or eight layers, let's say, along the other direction that go through. These are 30 millimeter diameter tubes with gas inside. This is what we call the monitor drift tubes.
They were produced partially in Saloniki and in Athens.
Yes, that's correct.
Yes, I would also like to, so I'm from Argentina. I don't know if I said that before, but so here in the, except for the US, we're not really used to work in this kind of experimental big detectors, right? And you mentioned that one of these were made in Chile, right?
Yes, the sTGCs, where they have this.
Yeah,
yes,
so
you see part of the sector, this part is made in Chile. Yeah,
exactly. So that's, well, it's really huge for us Latin American people. And it's really good to see that we can actually contribute from all countries in different ways. So I was also wondering, you talked about all the different testings that you had to go through before installing this, and that they were performed in different places, right? At Fermilab, DESI, somewhere else. So I was wondering if there is any test that you would like to perform, but it was not possible because the technology outside CERN wasn't enough. I don't know, for example, you want to test how this small width reacts when you have a big magnetic field, for example. Was it something that you wanted to test, but there was no possible because the technology was not enough, and you have to wait until the very last minute when you actually install the small winds on the cavern?
Yes, so this kind of tests, like the magnetic field and the performance inside an environment that has a high background radiation like the one expected in Atlas, this kind of tests we did from the beginning. We had to do because we need to make sure that the detectors really work in the environment that we are going to put them in. So I think actually most of the tests have been done. The thing right now that we are rushing a bit is, the testing of the detectors when we put them on the wheel. They have to go through some testing, which I don't mean that it is not done. It is just done. We are trying to parallelize it, and there we have a lot of people working on it. So it would be better if we had more time to do this. This is what I'm trying to say. And the other thing that we wanted to do and we didn't manage to do before the installation of the wheel is to take a sector from the wheel as the ones installed and take it to test beam. This is so take one of the sectors and put them here in the accelerators. And measure the performance for a long time. Do a test for a long time there, and we will understand a lot of things about this. So this we didn't manage to do before we installed the wheel, but it is planned to do it after the installation of the wheel, because we will it will be very useful for us in any case to understand better the actual detector, the new small wheel detector.
And you'll have to test this before run 3 starts, right?
It will be independently. I mean, we don't expect to find anything that is, you know, like a showstopper for the detector. It is really meant to gain experience and learn things that will help us optimize the performance when we will have it operating in Atlas. That's the main objective, because we cannot do this R&D while we are in Atlas and the detector is running with the rest of the experiment.
Yeah, exactly. Thank you. Well, I think Rachel has a question, or she raised her hand. So
yeah, thank you. I do have a question, if I may. Thank you, Kostas. It's been super interesting to have an insider's view of the journey that you've been on for the new small wheels. And I was wondering, what would you say has been the most challenging part of that journey that you've been on, from the conception to nearly having it up and running, if I can say?
That's a very good question. We had, I mean, it's always like this. All these projects, they have challenges and problems. You cannot predict all the issues you will face while you're going through this process. So I don't know if I'm able to really put the priority and on this and grade them, but for sure, you know, the problem with the noise that came up at the point where we were about to finish the wheel is the most striking one, because it had the largest impact, not only in terms of schedule. Okay, we lost 3 months. 3 months compared to 10 years, it's not a lot. But when it comes at the point where you are rushing to finish, it has a big impact, and it also had a big impact in our psychology, let's say, in our morale. So yeah, if you ask me now, I would say that was the biggest challenge.
But the thing is, as you had in your last slide, that the bigger the challenges to overcome, then the sweeter the what is it? The more glory you have. Yeah.
That's right. When you find the solution finally, it's so rewarding that it cannot be described. But before that, it's you feel like you're hitting your head on the wall. It's really bad.
That's life, isn't it? Nothing is ever really straightforward.
Yeah, exactly.
Yeah. It teaches you patience. Thank you.
You're welcome.
So how sorry, yes, go ahead.
No, Florencia, go ahead.
No, I was just going to ask, like, I see there's a lot of people working on this, but can you give us like approximately a number of how many people have been working on this?
Oh, that's super difficult because, you know, of course, in 10 years, people are coming and going, so I cannot really count all the people. And so there is, just to give you an idea, only for the activities of the integration, like the activity here, which is happening at CERN, for the Micromegas and the sTGCs, and for services, installation of the sectors, and the commissioning. Only for this, I think we have about 100 people working at CERN for this, only for this. But of course, you have to keep in mind that the detectors are not made at CERN, the chambers. They are made, as I said, all over the world. And there, I don't even know. I cannot even, predict how many people have worked on building these detectors. So it's a very big project with a very big collaboration, just for a small wheel.
Can I add a comment to the question made by Rachel?
Yes, please.
The micromega chamber, when they were invented, they had small dimensions. So the big challenge was to let this dimension go a bigger one. But in doing that, the ionization channel that is developing inside the chamber could be destroyed. And for here, the research community has tested many dimensions, and till when it has been reached the optimal dimension, which actually is used in Atlas. Is that correct, Kostas?
That's correct. That's what I meant with, you know, this R&D. It's basically, I mean, this is one part of it, but yeah, as you see here, for instance, you can see on the top left, these are all Micromegas detectors that are prototypes. So we started with these small 10 by 10 centimeter chambers, but inside these chambers, they have different characteristics, like the, you know, the size of the strips, the resistivity that is used for the resistive strips, and even the size of the gaps can be modified. And then we had other things while going through larger sizes. So you see here that we started to have larger chambers, which again have different characteristics. So all this activity was about, you know, testing different detectors with different characteristics and converge on the one that is that we can build it first of all in a large size, and then that it satisfies the requirements for the detector. This was also a huge R&D work that we went through.
Also for electronics, because the Micromega chamber, they are covering high eta, and at that point the intensity of radiation is quite high. So we have to develop radiation resistant electronics.
Exactly. We have we know from simulations what is because okay, we have measurements as well, but you know, for HL-LHC we needed to simulate what will be the radiation expected in that area, and then the electronics that were made, they had to go you know, through irradiation tests where they were put inside either you know, neutron reactors or other places where we can simulate the noise, the background radiation, and make sure that, you know, we keep monitoring them for a long period while we have the irradiation, and make sure that they keep working and there is no problem. Of course, this is one of the requirements, that of course the electronics, they need to be radiation hard, otherwise, because if you lose the electronics, basically the detectors are useless. You cannot do anything. So electronics are equally important as the chambers in these projects.
Okay, thank you, Kostas. I think that if there are no more questions, I will just hand it back to Rachel so she can close up the meeting. And again, thank you a lot for the question and the interest, and mainly to Kostas for the really nice presentation and the hard work all over these years.
Thank you, Florencia, and also thank you, Kostas. Yes, really impressive. And I don't know if you've been looking in the chat, but there's plenty of people who say that your presentation has brought back great memories of when they were at CERN and at Atlas. So a really, really big thank you. And perhaps you can come back and give us an update on the progress in, I don't know, maybe a year's time, or I don't know when would be the optimum time, but perhaps we could look into that and we'll tune in again. So very, very, very big thank you. Congratulations for everything you've done. And thank you very much as well to Florencia for doing such a great job at moderating. Thank you to all of you for tuning in. And I'm pleased to say, before we all say goodbye, the next News from the Lab will take place on the 3rd, so Thursday, the 3rd of June, and we'll be focusing on accelerators for society. So thank you very much again. It was wonderful. And I think if you've got any questions for Kostas, I'm sure that you can probably drop him a line, if that's okay, Kostas, or you can send it to me.
Feel free.
Yeah, thank you. And this recording will also be made available, so you can watch it again. So very big thank you to Kostas and Florencia, and then to everybody else for tuning in. And have
Thanks
a lovely
for having
evening.
me.